U.S. commuters spend an average of 42 hours every year stuck in traffic jams. The Texas Transportation Institute estimates U.S. highway congestion costs to be at $160 billion a year. Lost productivity, gas burned while idling in traffic, and additional wear and tear on vehicles. Our model tries to determine how we can reduce urban emissions by minimizing commuter traffic by looking at one of the most packed roads in the Bay Area, the Bay Bridge. The main cause of congestion is the toll booths. Attempts to reduce congestion on the bridge include the implementation of fast track and incentives to carpool with high occupancy vehicle lanes, otherwise known as HOV lanes. However, designating more fast track and HOV lanes might increase the congestion in normal lanes, overall increasing emission. Using the simulation software Sigma, our team of industrial engineers has identified 3 important questions about congestion mitigation we'd like to answer. First, we consider how many HOV lanes are optimal during rush hours: 0, 1, or 2 lanes. We also consider whether the minimum number of passengers required to use an HOV lane should be 1 or 3. And last but not least, when one of the lanes is temporarily closed due to accidents, road repairs, or construction, how should the remaining lanes be designated to limit congestion? In order to generalize our model to any bridge, we use data from traffic research to project the changes in volume that result from changing lane designation and requirements. We then take a moving average of traffic volume input given hour by hour to simulate arrival times and define service times for fast track and cache lanes according to accepted distributions. This allows us to simulate wait times, which we can then convert to average speed, average carbon emissions per vehicle, to allow transportation planners to make decisions which minimize emissions. Our event relation graph models arrivals and service times for multiple lane types and classic queue systems. For our example simulation, we use Bay Bridge data to model arrivals for HOV, cache, and fast track lanes. We also model lane failures, such as accidents, as events which correlate to lane types and frequency proportional to the traffic. The final piece of our model is keeping track of the hour, under the assumption that we will be using hourly traffic volumes as input data. After running several simulations, we found that HOV lanes don't actually improve the overall gas emission, and that 2-passenger minimum carpool is much better in terms of gas emission than 3. And lastly, in the event of an accident, most optimal strategies have no HOV lanes, and instead an even balance between normal and fast track. In order to further improve the accuracy and practicality of our current model, we have identified the following areas for modification. Our current model employs a linear deterministic inter-arrival rate. Considering the non-stationarity of our model, employing a probabilistic beta distribution to model the arrival rates may result in a more realistic depiction. In the case of certain type of lane being closed due to unforeseen circumstances, our model can be further improved for lane redesignation given the dynamic and non-stationary nature of traffic. Our model is expected to do a decent job in simulating traffic on freeway segments, where there are designated lanes for different purposes. However, such a model can be difficult to be applied on other roads, such as local roads.